thank you everyone for tuning in to watch this student seminar. First of all, can you see my mouse? Yes, okay, perfect. So yeah, I am Garvin Yim. I am from the University of Southampton. I'm a fourth year PhD student, and I am currently being supervised by Ian Jones. At the end of this year, I'll actually be doing my first postdoc at the Kavli Institute at Pekin University. So there's a good chance that I might see one or two of you next year. Yeah, hopefully I can continue being part of this this group next year, but over from the other side, which would be quite nice. Okay, today I will talk to you about modeling small glitch-like events as neutron star F-mode oscillations. So first of all, let's look at what I mean by pulsar timing irregularities. There are generally two types of pulsar timing irregularities. We first have the idea of glitches. So neutron stars, as we know, are very good clocks. You can time them very well. However, every so often, the neutron star is seen to rapidly spin up for no apparent reason. It just randomly increases its spin rate in one part in a million, roughly. And normally there's an exponential recovery afterwards. This exponential recovery is not seen all the time, but most of the time it is. And at the same time, the spin down rate, so you can think of this as the gradient of the frequency, becomes more negative at the time of the glitch as well. And so kind of the simultaneous change in the spin frequency and the spin down rate is what we classify as a glitch. Now, if we go back to the idea of the spin of a neutron star being well timed, once we subtract out what we know about the spin frequency, we're left with some spin residuals, and this is what's shown here by this wiggly line here. And these are very long period oscillatory or quasi-oscillatory features, and this is what's known as timing noise. The period is typically, more than a year or so. So these gaps here, these peaks are separated by quite some time. If we take a Fourier transform of the residuals, such that we can break it down into its frequencies, we see that timing noise is a very red spectrum behavior. So we have a lot of power down in the lower frequencies, and no one truly knows what the reason for timing noise is. As the name suggests, it's kind of a noise, and we can't fully model it yet. However, a lot of us believe it's something physical because the noise is not white, as in it's kind of pushed towards the red side. So I'm looking to perhaps model timing noise with these F modes. So more recently, there was a pair of papers by Espinoza et al. Who tried to maybe distinguish between timing noise and glitches. What they did was they created a automatic glitch detector and applied it to the data of the crab and Vela. And when they ran their automatic glitch detector on the data, they managed to recover all but one of crab's glitches, but they also uncovered a whole population of smaller phenomena where these black dots here, glitch candidates, these are positive changes in the spin frequency, but negative changes to the spin down rate. Likewise, they swap the signs around, so anti-glitch candidates are negative changes to the spin frequency and a positive change to the spin down rate. And we can see that these glitch candidates and anti-glitch candidates, they're fairly evenly distributed in this parameter space here, where we've got changes in the spin frequency and the spin down rates. And a very similar population was identified in Vela too. And this small population of small events it is a physical phenomena because the detection limits are kind of shown by these shaded regions. And so they found something that's physical, but they don't quite know what it is. They suggested that it could make up timing noise. And this is kind of the idea which we'll be running with. Okay, so in our model, the key idea is that timing noise is caused by lots of small, perhaps unresolved glitches. This is not a new idea. It's lasted since the 1980s. And the cause of these small glitches are due to F modes being excited. And these F modes would emit gravitational waves. Now, you can think of F modes as like bulk changes to the shape of the neutron star. So you might think of a neutron star mountain, where it's like a L equals 2, M equals 2 deformation. And this kind of spins around. So it's like a rugby ball shape spinning around on an axis. And the only difference between these F modes and neutron star mountains is that these F modes typically last only about 10 milliseconds or so, whereas a mountain would last a quasi-infinite amount of time. So I've got a pictorial kind of representation of the model. But we start with a rotating neutron star, and it typically spins down on the order of a month or so. The month is because this is how frequent these glitch candidates and anti-glitch candidates occur. And during this spin down, the elastic energy gets stored in the crust of the neutron star. However, once the elastic limit of the crust is reached, the crust will crack, and this could excite some F modes. In particular, it could excite prograde F modes. So these are F modes that move in the positive sense, and retrograde F modes which move in the negative sense. And like I said before, these F modes would emit gravitational waves, which is represented by these lines here. And when we inject angular momentum into these modes, we must take some away from the bulk of the neutron star. So if we excite a prograde mode, we must slow down the neutron star slightly, just to conserve angular momentum. And then finally, we have the decay of the mode. And this will take, as I said, roughly around 10 to 100 milliseconds. What we found, which was quite counterintuitive, is there's such a thing as a gravitational wave back reaction. And what I mean by this is, if we imagine a non-rotating neutron star, which has a prograde mode on it, then the decay of this prograde mode will actually cause the neutron star to start spinning in the retrograde direction. So this is what we call the gravitational wave back reaction, and we kind of found it when we conserved energy and angular momentum. So that will play a small part in changing the spin frequency of the neutron star. Okay. So the F modes, we used a particular kind of F mode called Kelvin modes, and these are basically just modes on a uniformly dense, incompressible, and static neutron star. The assumptions are there just to simplify all the equations. It also means all our work can be done analytically. As for the static background assumption, so long as the neutron star is rotating slow enough, this is an okay assumption, because any corrections would be on the order of omega over the breakup frequency, which will only be small. We also did it in Newtonian gravity too, just as a proof of concept. So we have our eigenfunctions here. This xi is basically just how much a fluid element gets displaced by, and this depends on its position within the neutron star. And we can see that each fluid element, it oscillates at frequency omega L, where omega is given by this expression here, which are the eigenvalues of the problem. And we can see that for L equals 0 and 1, we would get, well, we wouldn't get oscillations. And so the lowest non-zero eigenvalue happens when L equals 2. So we'll focus on that here. L equals 2 happens to be the strongest emitter of gravitational waves too. And so we'll only just focus on that one. If we take a factor of e to the im phi out of the spherical harmonic, we see that the mode eigenfunctions go as e to the I m phi plus omega t. And so since this is the phase, we can track the phase of the mode to just a fixed phase of the mode, and this gives us our pattern speed, and it's defined as minus omega over m. We can see that when m is equal to a negative number, so say m equals -2, we would get a positive pattern speed. So using the eigen functions, we can calculate the amount of energy and angular momentum in the modes. In the past, the energy was taken as the canonical energy and angular momentum as the canonical angular momentum. And these are expressions which you get from Lagrangian mechanics. However, there was a slight issue with this because back in 1978, in their famous paper, they discovered that you can add a what they call a trivial displacement to these xi's, and what that did was it actually changed the value of the canonical energy. However, if you actually look at what it represented, it represented a relabeling of fluid elements, which is not a physical thing. Like you can simply swap A and B round, and it would change the value of the energy, which is not right, because the energy must be invariant, as we know. And so to counter this, they did a full derivation and found that you needed like an extra integral as well. And once you include this extra integral, you get the physical change in the energy. And this is invariant with respect to these trivials that I mentioned. The same happened for the angular momentum too. So once we calculate the energy and angular momentum of the modes, we can also calculate the rate of change of energy and angular momentum due to gravitational wave emission. And that's just given by these standard quadrupole formulae. And then if we just take the ratio of the two, so if we just do the energy in the modes divided by the rate of change in energy, this will give us the energy timescale. But because we're concerned about the damping timescale of the modes, we introduce a factor of 2 here because the energy is quadratic in the amplitude. And you know, most of the literature, they only use the energy arguments, but there's absolutely no reason at all why we can't do the same with angular momentum. So this is what we did. And because the two methods should give the same answer, you know, this is something that we can test against. However, when we actually do the calculation, we find that the angular momentum timescale is half that of the energy timescale. And this is not right. We need to have the timescales matching. And so how do we solve this? We could say that the gravitational wave emission from an F mode causes the neutron star to start spinning. And what this does is it changes the angular momentum to linear order in omega, but it won't change the energy, which is quadratic in omega. So long as this back reaction doesn't spin the neutron star fast enough, this is a okay assumption as well. So now we allow for a back reaction. The angular momentum will now be made up of the angular momentum of the bulk, which is just I omega, plus the angular momentum of the modes, which is delta omega. Taking the time derivative of this and ignoring the I dot term because the moment of inertia doesn't change that much over the timescales considered here. We can write the rate of change in the angular momentum as the angular momentum divided by normally the tau j, the angular momentum timescale. However, we saw before that it was different to tau e, So now we're going to force it to equal tau e, which is what I've done here. That's why the denominator is tau e. And we can substitute in our equations. On the whole system, we only have a gravitational wave torque spinning down the entire system. And previously we calculated delta J and tau E, so substitute that in as well. Then rearrange for I omega dot. And what we find is that omega dot is non-zero. This means that because of the decay of these modes, we will get some sort of spinning effects on the bulk of the neutron star. And we can see it's a negative half of whatever is lost as gravitational waves. So if positive angular momentum is being lost as gravitational waves, this is positive. And so omega dot is negative. Okay. And the total change to the angular frequency, it's comprised of two parts. Like I said before, at the moment of excitation, the neutron star must lose a little angular momentum in order to excite, say, a prograde mode. But then we also discovered that the decay of this mode will cause a back reaction. And so we have the two effects adding together. And once we add them together, we find this here. And the change in angular frequency will be step-like so long as the excitation of the next mode happens much later than the decay timescale of the modes. And this is fine because the timescale until the next mode is about a month or so, but whereas here we said is around 60 milliseconds. Okay, so here we've shown that just with one parameter, with alpha, which is our initial mode amplitude, we can determine the change in spin frequency. However, we saw earlier on that we also need to explain the change in spin down rate. So how do we go about that? Or when we calculate it, we find that the fractional change in the spin down rate is about 100 or 1,000 times larger than the fractional change in the spin frequency. And if we take the typical methods of spin down, so this is any sort of spin down mechanism where the spin down rate is proportional to the spin frequency to the power of n, where n is the breaking index, then we find that this relation is true. And because n typically is less than 7, we can see that these standard methods of spin down account for this large disparity between the two values. So instead, because in reality we know that a neutron star is made out of a superfluid component and a normal component, and between the two components there's a coupling torque. So if the crust is spun up a little due to our mechanism earlier on, then the coupling torque will act to spin it down again, and so this would increase the spin down rate. And once you work through the maths, you'll find that the fractional change in spin down rate and the fractional change in spin frequency are related by two lots of the characteristic timescale, or the age of the neutron star, divided by the coupling timescale. The coupling timescale is typically taken as the glitch recovery time after glitches, and this is normally about a month or so, whereas the age of a pulsar is typically about 1,000 or 10,000 years. And this gives us our necessary change in spin down rates. So we can apply our model to the data. First of all, so there's two parameters in our model. There's this coupling timescale and the initial mode amplitude. The coupling timescale, like I said, we can take as the glitch recovery timescale, and this is a very normal thing to do. And if we, so you can just go through the literature and find the range which we get here. The smaller the coupling timescale, the greater the change in spin down frequency. So the smaller values give us this upper boundary here, whereas the larger value gives the lower boundary. And then what's left is our only free parameter, which would be alpha, our initial mode amplitude. And with an appropriate selection of alpha, so if we select one large enough, we'll be able to explain the largest of the small events. And that's what's given by this vertical line here. And all mode amplitudes smaller than this large value will explain everything which is towards the left here. And so with a appropriate selection of alpha and tau, we can explain anything within this red box here. And you can see that it remarkably models these small glitch events. And we've done the same with Vela too. Okay, and I think the last thing to say, I've not focused too much on the gravitational waves yet, but you can do the calculation to calculate the signal to noise ratio that you would expect for these F modes. And at least for one of these F mode oscillations for the crab, we would expect a signal to noise ratio of about 2.3 for the Einstein telescope. And this is far below the threshold to call it a detection. Whereas for Vela, it's a little better. For a single event, it's about 10.3 or so. It's still not quite high enough. However, because we can model these, and the signal to noise ratio improves as the square root of the number of events, we could perhaps stack 2 or 3 of these events to increase the signal to noise ratio. And that should give us enough signal to noise ratio to either disprove or enough signal to noise ratio to test this model. So I'll just finish with my summary now. So we have shown that small glitches and anti-glitches can be caused by the excitation decay of retrograde and prograde F modes. The change in the spin down rate of these events is explained by a coupling torque within a 2-component model. The decay of a prograde F mode due to gravitational wave emission causes the neutron star to rotate in the retrograde direction. And this is what we call the gravitational wave back reaction. And the model will become falsifiable with the Einstein telescope. For future plans, we look to calculate from first principles what the initial mode amplitude would be for the build-up of energy between events. We'd also like to explore where the back reaction would have a large impact. And we'd also like to remove some of the assumptions of the model. But if you have any questions, please ask, and thank you for listening. Does anyone have any questions?
Thank you, Garvin. I should say that, so I think we maybe have time for one question. So if there's any questions, Patrick has a question, so go, Patrick.
Hi, Garvin. That was really, really interesting. Thank you. I'm just curious, the results for the Vela pulsar on the previous slide. Your sort of pink region for crab, it's like exactly fits basically all of the points. But for Vela, it's a much larger region and it's less populated. Do you have any idea why that's going on?
So I think I can tackle the last question first. It's a little less populated because the timing residuals for Vela are a bit more noisy, and because it's more noisy, the authors can't claim that they've detected one of these glitch candidates or anti-glitch candidates, which is why there's fewer events here. Also, I feel like they have more they have data for the crab from like ages ago, whereas for Vela, it was only timed to the correct precision kind of much later. So the time frame of the data is much shorter. And as for kind of the red regions not explaining, well, for example, we have like a larger gap here at the bottom. This is only because of the ridiculously large values of the coupling timescale. I think for Vela, the vast majority of glitches do recover slightly shorter than 1 year. What we have here is the entire range of the coupling timescales that I could find in the literature. So it could be that, say, like you can think of this as like a distribution. You could think that most of it is it's more skewed towards the lower values of tau. But I've literally just taken the range. So I took the very largest value of the coupling timescale, which is why this bottom line is so much further down. Yeah.
Great, thank you.
Okay, thank you.
Thank you, Patrick. I think we should all say thank you to Garvin.
Okay, thank you.
And thank you so much for the talk. And I think we'll give the floor to Yun Fang now from the University of Pekin. Thank you.
Okay. Can you see my screen? Hello?
Yes.
Okay. Hello. I am Yun Fang, and I'm from Kelvin Institute for Astronomy and Astrophysics at Pekin University. Actually, I'm now a postdoc in Xianchen's group, and this talk is about the gravitational radiation from the binary-EMRI system, based on these works, which has finished, and one is being is under preparing. The binary black hole formation near a supermassive black hole in Galactic nuclei has been conducted since 2012 by Macarena and Antonini et al. According to the recent studies, that the AGNDs could form the binary black hole in a close orbit to the supermassive black hole, typically by dynamical binary and gas capture binary formation channels. This is a configuration of the binary-EMRI system. In the weak interaction cases, when the binary is in a relatively large distance from to the supermassive black hole, the dynamics is dominated by the Newtonian and the post-Newtonian evolutions. If additionally the binary orbits have a relatively large inclination angle, the binary black hole will move and cause a Kozai-Lidov oscillation. And if in the strong interaction cases, when the binary black hole is in a much closer orbit to the supermassive black hole, it becomes a black hole perturbation theorem problem. Sorry. Next, I will briefly talk about the dynamics and the gravitational waves of the binary-EMRI system in the weak interaction and the strong interaction region. Firstly, the weak interaction region. The equation of motion of the binary black hole is dominated by the Newtonian gravitational force, which causes the Kepler orbits. And the second term is the supermassive black hole theta force, which causes the Kozai-Lidov oscillation of the inner binary. In our case, that the supermassive black hole mass is much larger than the inner binary, thus the total orbital angular momentum of this system is dominated by the outer orbital angular momentum. And the conservation of the total orbital angular momentum will lead to the projection of the inner orbital angular momentum along the outer orbital angular momentum to be conserved. And this conservation will lead to the exchange between the inner orbital eccentricity and the inclination angle, which leads to the Kozai-Lidov oscillation. And the post-Newtonian effects are also important for the second evolution of the binary black hole supermassive triple system. the relativity precision describing by the precision of the axis, and the Kozai-Lidov oscillation depends on this angle by proportional to sine 2 omega. So if the precision time scalar of the omega is much smaller than the Kozai-Lidov oscillation time scalar, and then the Kozai-Lidov oscillation will be averaged out by the faster precision. Since all the observations indicate that most of the supermassive black holes have large spins, which the figure I'm not showing here, but it is a result from the observation of X-ray spectrum. And so we considered the supermassive black hole spin effect at 1.5 post-Newtonian order. The reason for this consideration is that in this case, the total orbital, the total angular momentum of this triple system is mainly dominated by the spin of the supermassive black hole. And in this case, the outer orbital angular momentum is placing around the spin of the supermassive black hole due to the length straining precision, and the inner orbit will precede in a much more complex way. Since in the standard Kozai-Lidov formula, it is assumed that the total orbital angular momentum of the triple system is conserved. So, but in the presence of supermassive black hole spin, the outer orbital angular momentum is now the total orbital angular momentum is now not conserved anymore. So we need to extend the Kozai-Lidov formula to a more generalized case, to including the precision of the outer orbital plane. And we derived this generalized Kozai-Lidov formula, which tends to be depend on the relative angle between the two orbital longitude of ascending nodes, and also the inclination angle of the outer orbit angular momentum and the spin angular momentum. And it will naturally degenerate to the standard Kozai-Lidov formula by setting the inclination angle to 0 when it is conserved. And due to the evolving of the outer orbital plane, there is another first post-Newtonian effect, which will couple into the secular evolutions. And that is the theta precision due to the interaction of the three bodies. There is the typical modulation of the Kozai-Lidov oscillation due to the supermassive black hole spin effect. That is, these precision effects will cause the projection of the inner orbital angular momentum into the outer orbital angular momentum to evolve, which is conserved in the standard Kozai-Lidov formula. And it evolves due to the supermassive black hole spin this way. And the maximum eccentricity excited by the Kozai-Lidov oscillation is related to this conserved quantity by this form expression. Next, I will move on to the characteristics of the gravitational waves in the binary black hole supermassive black hole system. The gravitational wave in this triple system has been studied by Maron since 2017 by studying the multi-band observation by Lisa and LIGO Virgo. Horn et al., Randall and Xianyu has started the detection of the increasing of the binary black hole eccentricity by the detection of Lisa. The peak frequency of the gravitational wave describing the maximum radiation power corresponding to the frequency. And it is closely related to the eccentricity. And this figure shows the excitation of eccentricity due to Kozai-Lidov mechanism. And this zoom in is the details of the increasing and decreasing of eccentricity. In the lower panel, it shows the increasing and decreasing of SNR due to the increasing and decreasing of eccentricity. In our work, we compared two waveforms with the spin and without spin effects. These waveforms are quite different, even from the first 4 years evolution. And we proved that in this case, the waveforms is distinguishable by Lisa, with the fitting factor lower than the threshold value. In another example, we give the detection ability of Lisa by the difference of the maximum eccentricity between the first two peaks. This is the variation of the excited maximum eccentricity due to spin effect. And in the lower figure, it is the corresponding peak frequency. And the difference of the maximum frequency could be 10 to minus 3 Hertz. And the difference of the signal to noise ratio is 23 in this case. Thus, this is a way to degenerate the supermassive black hole spin effect in the binary black hole waveforms. In the last, we will move on to the strong interaction cases, which is described by the black hole perturbation theory. And the gravitational radiation in this case is described by the function called phi4. It is obtained by solving the Tarkovsky equation. The wave function could be decomposed into the spin weighted minus 2 spin harmonics. Then the Tarkovsky equation will degenerate into the two functions, two equations of motion. Into the two equations. The first one is just the eigenfunction, and the second one is about the radial Tarkovsky equation with the sources. It is proved by Chandra Sekhar that the radial function could be changed into, could be transformed into the Regge-Wiener equation, which is the static Schwarzschild case, and it could be solved by green function method. The the wave function is must satisfy the ingoing condition at the event horizon and the pure outgoing condition at the infinity. The source, the portal beam source, is described by a binary black hole, described by 2-point particles here. And the waveforms in the strong interaction situation was firstly conducted by Cardoso et al. They find that there is a resonant excitation of the supermassive black hole quantum mode. That is the gravitational tuning force effect due when the binary, when the frequency of the binary is equivalent to the supermassive black hole quantum mode frequency. This shows the excitation of the energy flux at infinity due to the resonant due to the resonant effect, and the waveforms in this binary-EMRI system also shows the gravitational lensing, Doppler shifting, and the beaming effect shows in the right figure. We are currently working on this project, and we have already have some results, but the paper is not finished yet. Yeah. Finally, is the conclusion. This talk gave a brief introduction of weak interaction binary-EMRI system and the strong interaction binary system in the different dynamical evolution behavior and the gravitational radiation. There is abundant gravitational radiation phenomena in this binary-EMRI system, and also abundant astrophysical applications. Let's talk about end up here. Thank you for your listening.
Thank you very much. That was a great talk. Thank you. Do people have any questions?
I have a question. Sorry.
Yeah.
Because I'm host, I can't put up my hand. It's strange. Anyway, I have a question about the your description of the spin effect as a supermassive black hole spin effects. When you were showing the so just so I understand, the red is with the spin effect and the blue is without. Is that the difference?
Yes.
I see. Okay. And so you're suggesting that if we are able to detect a change in the resonant peak of about 1 millihertz and a change in the SNR of about 23, then this is an indication that there's a supermassive black hole spin effect imprint on the BBH system. Is that right?
Yes. Here in this example, the change of the maximum eccentricity is purely due to the supermassive black hole spin.
Okay. I'm just trying to think about what the absolute frequency would be. I mean, this is a function of the mass of the binary black hole, I guess, but roughly, what scale would it, I guess?
Oh, In this figure, the time scale between the two peaks is 4 years.
Okay.
Yeah.
So at some point, okay, we might be able to. We have to see. Okay. Okay. Thank you. And then I have a question about the strong effect. So where is it? I think it's the next one.
Mm-hmm.
Sorry. Yeah. So this plot on the bottom right,
Yeah.
is that the expected waveform for the BBH, which has been which is after the strong interaction? Is that the expected signal?
This black line is when the observer in the equatorial plane, when theta is pi/2, and when the gray line is when the observer is face on with the out binary plane.
I see. So okay. Sorry, I did not see the angles. Yeah.
So when in the face on case, there is no lensing Doppler effect because they are the same. They have the same velocity to the observer, but when the observer is edge-on with the outer orbital plane, the outer orbital motion is moving very fast. So there will be Doppler effect and also the strong gravitational lensing effect, because when the waveform, when the binary moves back to the black hole, the lensing effect will be large.
Okay, thanks. I understand now. Thank you very much.
Okay.